section 14.1, we're going to learn about limits of functions, and in this section we're going to just use the informal definition of a limit. And what that means is that basically we're just going to, instead of finding the limit of functions, we're just going to find strong evidence of what a limit of a function might be a certain value. So we're actually not going to prove that the limit of a function is equal to a certain value in this section. That'll come later. Okay, so up until this point, most of the math problems that you dealt with involve the behavior of a function at a particular value. For example, you may be asked to find the value of a function f of x when x equals c. So, for example, maybe I ask you to find, I tell you that f of x is equal to x plus 3, and find the value of f of x when x is equal to 2. And then you know that the answer there is 5. Now, the underlying idea of the limit is that we're looking for the behavior of the function near x equals c. So it's not actually what happens where x equals c, it's what's happening as x is approaching c. And so here we have an example. I'm going to move on so that we can see it better here. So suppose you and your friend are walking along the line of the graph of a line f of x equals x squared minus 4 over x minus 2. Now, from what we've studied previously, you know that this function is not defined at x equals 2, and that's because there's a hole in the graph that would produce a 0 in the denominator, and it would be undefined at that point. So here you can see you and your friend walking, and you see where it is undefined here. So what we want to figure out is what's happening there. We want to know what's happening as we are approaching c, and that's where these values here come from. Okay, c being 2 this time. So what's happening as we're approaching 2? And so the first one, okay, here's our line. So the first is as we're, and here's our hole, as we're coming up to, because then x would be increasing, and then the next is as we're coming this direction, and so those are here. And we're going to need our calculator to take a look at this. So let's go ahead and pull up our calculator. So you're going to need to make sure that your calculator is in function mode, and we're going to graph this function. Okay, moving a little slow. Okay, so we're going to go to mode, make sure we are in function mode, and then go to our y equals. Let's put in our equation, and we have parenthesis x squared minus 4, parenthesis divided by x minus 2. Got to have parentheses there again. Okay, now I'm going to do a zoom sticks to a standard viewing window, and we see we get that line. Now you notice that it's not producing that that hole in the graph. The way you can get your calculator to do that, if you actually put that hole in the center, you know the hole is going to occur at x equals 2. So if we go to our window and maybe go to maybe 4 to the right of 2 and 4 to the left of 2 is going to give me a minimum of -2 and a max of 6x, and let's try this graph and see if we get a hole. Okay, there you can sort of barely see the hole now. You'll be able to see it a little easier probably on your own calculator, but you can barely see the hole now on this graph. If you trace, then you should be able to find that it's actually going to pop up. That should be the first value now that we've put it in the center, because if x equals 2, you see now that y is undefined, and then we can move along here and see what's happening. So this allows us to see what's happening. Okay, so let's move up towards where x equals 2. You see x is approaching 2, and what's happening to y? You should be seeing that y is approaching some number. Okay, now let's try it from the other direction. I'm going to move out for a bit, and then let's move back towards x equals 2, and you notice that y is approaching some number here. Okay, so we can get a closer look by maybe going to the table. We're going to hit second table set, and we're going to have our table start at 2. and then we're going to have our table changed by 1, but in the independent here, we're going to change this to ask, so we can put in some values that we would like to put in. And let's go to our table, and let's change this to so I can see both screens at one time, and we're going to go through and look at the values that we would get here. So the first value that I have on my chart is 1.99, so I'm just going to start putting those in, and we're going to see what happens. So at 1.99, y is going to produce 3.99. So then 1 point. Okay, and okay, so you see what's happening. And then I'm actually going to put in 2. And we do get an error because it's undefined there. I'm going to put in 2.0001. See, it's you should notice by now that they're approaching 4. And okay, so there you have your values. And with this, we can now go back here, and it says, well, what's happening as x is getting closer to 2? And we saw from the work we did here, as x is getting closer to 2, y is getting closer to 4. And let's change that to y is approaching 4. There. And then the notation for that, and that's actually what a limit is, it talks about what's happening as x is approaching 2. And the notation for this is here, and this would be read that the limit of the function f of x as x approaches 2 is 4. And again, we're not going to say that it is 4. We actually just have strong evidence that the limit of this function is, as x approaches 2, is 4. So what we've talked about so far is just the informal definition of a limit. So here's the informal definition of a limit. If f is a function and c is a real number, such that f of x is defined for all values of x near x equals c, except for possibly at c, which is like the example that we just did, where it was not defined at x equals 2. Suppose that, well, first of all, whenever x takes a value that's closer but not equal to c, on both sides of that, the corresponding values of f of x are getting very close to and possibly equal to the same real number. And in the last example we did, that's what was happening. Both as x was approaching 2 from the smaller side and going up, it was approaching the number 4. And as x was coming down from the greater side and approaching 2, it was also approaching 4. So let's just go back and take a look at that for a second so that you understand. So here you notice, here on your table, you see as x is approaching 2 from 1.99, 1.999, and so on, y is approaching 4. And then as we go 2.01, 2.001, 2.0001, again, we have y approaching 4 in that case. Okay, so that's the first thing that has to happen. And then the second thing is that the values of f of x can be made arbitrarily close to L by taking values of x close enough to c but not quite equal to c. So arbitrarily close, basically that means we can make the f of x get as close as we want to 4 without actually equaling 4 by just changing the x values and making them closer and closer and closer to x equals 2. So the limit of a function f of x as x approaches the number L, which is written as this here. And that's the notation that we need. So when we're using a calculator to find limits, we're actually not finding the limit. We're just finding strong evidence that of what a limit actually might be of a function at a certain at approaching a certain value. So it's very important to understand that you're only making a suggestion. The proof part and evidence is going to allow us to say that what the limit might be of a function as x approaches c is going to come in later sections. So in this case, what we're going to do is we're going to look at the sine of 3x over x, and we're going to find the limit of this function as x approaches 0. And we're going to use our calculator. Again, we're finding evidence of this. Um, so in our calculator, we're going to graph that. Just leave that first one in. And this time we have the sine of 3x over x. And to get started here, I'm just going to do a zoom trig, which is number 7, and take a look at what I have. Okay, now this time we're talking about approaching 0. So let's actually make ourselves a table here. And in the table, we're going to put in the center of the table 0, because we want to approach 0 from the negative side and from the positive side. So we're going to put 3 places on each side, and we're going to start out with negative 0.1, negative 0.01. So you notice we're getting closer and closer to 0. Okay? Then we're at 0, and then we're going to go on the other side of 0. Okay? And we're going to use our calculator to find those values. Let's go back over here. Okay, so you can see where at this point on the y-axis where x equals 0 and see where it hits. So you might have an idea of what it might be. You can also trace your function here to see what it is. And you saw that it is actually going to give us at x equals 0, it is undefined again. So that's something you would want to include on your table. So when we do this, let's go ahead and probably, you might want to get a better graph of this. And if you do, just go to your window. We don't need to go out to negative 2 pi is basically what it is. We don't need to go that far out to in the negative direction, nor do we need to go that far in the positive direction. So let's just change this to something like negative 2 and positive 2. And you can see the graph that we have here, and you know, you can, let's see, let's change that to positive. Okay. Now it should adjust for us. Okay, there we go. We have a little better graph now. You could take off a little bit in the y if you would like to. So our minimum, let's just change that to negative 2. And now we're going to go to our table and see if we can find some values. All right, so this time we are approaching 0, so we're going to change this to negative 0.1. Okay, we get a value in there, negative 0.01. Negative 0.001. Oops. Okay. All right. Okay. And now I'm going to go ahead and put in 0. I get 0, and this should make sense to you because this would mean that we had 0 in the denominator of a fraction and it's undefined. So we get an error there. The function is not defined there. So now we're going to go on the other side of 0, 0.001, 0.01, and 0.1. Okay, so at this point you should start to see what we're looking for. So we have pretty strong evidence at this point that that our function f of x is approaching 3 as x is approaching 0, f of x is approaching 3. So let's take this and put it here. Okay. So what we're seeing right now with this table is that the limit of our function f of x as x approaches 0 is 3. That's what we're seeing right now. That's the pattern that we're seeing, or what we have evidence for. Okay, and now let's go ahead and talk about limits and function values. If a limit of a function f as x approaches c exists, then the limit may not be equal to f of c. In fact, f of c may not even be defined. And so I have several different cases here that are going to help you understand that. Let's say I'm looking at this first one here. You notice here we do have a function, and f of in this case, f of a is actually what it is. F of a is defined. It's defined here. And the limit in this case would be here. Okay? Here it is not defined, right? But we do have a limit. And then in this case here, it is defined. It's defined here. But as it's approaching, you notice from the negative side here and from the positive side here, it's not going to give us this. So when you look, this is our limit, whereas this is our f of a. So the point in this is to show you that f of a is not always going to be equal to L. And that's the case here, when L is the limit. So that can be different because the limit is talking about what is happening, not exactly at f of a, but as x is approaching a. So we have x approaching a here and here, and it's not going to give us f of a in this last example. Okay, here we have another example. This one we have a piecewise function, so this is going to be a little bit different. It's going to give us hopefully a little better understanding of what's going to happen here. So in this piecewise function, what we have is that f of x is going to be equal to 1 when x is an integer, but f of x is going to be equal to -2 when it's not an integer. So when we graph that, let's first go through and talk about when it is an integer. So let's scale our graph here. Let's say that's 1, 2, 3, 4. 1, 2, 3. And let's do the same thing on the y-axis. Okay, now that we have that, so we're going to produce a 1 when x is an integer. So x is going to be an integer here, and we're going to get the point. So when x is 1, y is 1. When x is 2, y is 2. When x is 3, when x is 2, y is 1. When x is 3, y or f of x is going to be 1, and so on. So when we have integer values, this is what we're going to get. And here, okay. Now, when it's not an integer, f of x is going to be -2. So that's basically everything in between. So we're going to have holes. We're going down to -2. The line -2 is going to be here. Okay, so we're working along that line, and we're going to have holes at certain points. So where we're going to have holes, it's going to be at the integer values. Okay, we're going to have holes at the integer values. Okay, and it's going to be solid where we have non-integer values. And this isn't falling right on the line y equals -2, but close enough for you to get the idea, I hope. All right, so in this case, we are looking for the limit of f of x as x approaches -1. So as x is approaching -1. So let's maybe look at the line x equals -1. And that would be here. All right, so we're talking about the behavior when it's approaching. So from the positive side, when it's approaching, that is in this area here. And from the negative side, I'm sorry. And then from the positive side, we're going here. So you see how you're getting trapped. You're talking about this area right here. where you're getting trapped. So what's happening in here as it's approaching -1. Now in this case, we know that f of -1 is going to give me 1. But when we're looking for the limit, then f of -1 is not necessarily going to be that. So I want you to think about that one, and when you come into class tomorrow, I want you to tell me what you think the limit of this would be here in example 2. And we'll talk about this to get class started tomorrow. All right, and let's look at another example. And in this one, we're going to do some work with some trigonometry. Okay, so the first thing you want to do is put this into your calculator. You have to be very careful because we do have a cosine squared there. So we're going to have to be careful about putting that one into our calculator. Okay. All right. So on this one here, let's go ahead and put in our function. We're going to have to start out with some parentheses because we've got to square that cosine. Cosine of pi x. Now square it. Minus sine. Okay, and I think we can do a zoom trig on this one too to get us started. You should see a good graph of this one. Okay, so we have a graph, but definitely probably a little more than what we need. We can cut some off of the top and bottom from the y and definitely off the sides. So let's go ahead and take a look at that. Let's just change this, and notice that our limit here is at -1, as x is approaching -1, so we probably want to take that in consideration. It might be nice to actually put that in the center. So if we're going to put that in the center of our graph, then we want to go a little bit to the right, a little bit to the left. So let's say we go from -4 up to 2. My window. And this is probably more than what we need here too. Let's try it. Let's change our scale to 1. That'll be easier to see. And our y, we're definitely seeing more than what we need to, even though it's not very big. So let's change that to -2 and this to +2. Now you can see what we have. Okay, so we're looking at the limit as x is approaching -1, and that's why we've got that in the center of our graph. Let's go ahead and take off a little bit more on the x. Let's change this to -3 and change this to 1. Okay. And here we go. You can see a graph here. All right. And I can trace those values and see what's happening. Again, we're approaching -1, so let's go back and think about a chart that we need to make and what values we need to find. So we're going to go here. Okay, so when we're doing this, we're talking about approaching -1, so we're going to approach it from both sides. And here we get -1.1. We could say -1.01, -1.001, getting closer and closer to -1. And then on the other side, okay, so we're looking for those values there. So I'm going to second table, going to put my values in. Starting out with okay. Okay, I'm going to go ahead and put in -1. And this time you notice that it is defined. put in a negative when I should. Yeah, that's right. I do need to put in a negative this time. Okay, here we go. So we definitely have some evidence here, some strong evidence that what's happening is that it's approaching -1. Now, this is the first example that we've done that in which we notice that the limit is actually the same as f of -1. F of -1 in this time produces a -1. It's not undefined. So what you're going to start to notice is that for many of the examples we do, and mainly the polynomial rational functions, if f of x is defined at x equals c, then the limit of f of x as x approaches c is going to be f of c. So in this case, what we found is evidence that the limit of f of x as x is approaching -1 is -1. Okay. All right, sometimes there are actually three different situations in which a limit is not going to exist that we're going to talk about. This is the first one, and it's when f of x becomes infinitely large or infinitely small as x approaches c from either side. So in this case, I may have been asking to find the limit as x approaches 0 of the function. Find the limit of the function 1 over x squared as x approaches 0. So here you can see the graph here in blue, and we have the line. Here's where x equals 0. Now, as x is approaching 0, then what's happening? What happened is this is getting infinitely large in this case. So you would say that this limit does not exist, because f of x is becoming infinitely large in this case. All right. So the next example is going to be when f of x approaches L as x approaches c from the right, and f of x approaches m with m not equal to L. So basically what you have happening is it's easier to look at a visual of this rather than what I've just read to you. But if you think of these little bullseye marks here being holes in the graph, and as we're approaching x here, we're approaching this value, which maybe it's a y value of -1, let's say. But as we're approaching from here, y is approaching +1, or f of x is approaching +1. So this f of x, these two different values here, are what we're talking about being L and M. And you notice that L and M are not equal to each other. So in this case, the limit would not exist. And this function here is the graph of absolute value of x over x. And so we're saying that this one does not exist. Okay. And then the last example is going to be when f of x oscillates infinitely many times between two numbers as x approaches c from either side. So here we have a function. F of x in this case was sine of pi over x. Now, so you might graph it the first time, and you notice this first graph I have here is between -20 and +20, and you say, okay, well, maybe I need to take a closer look at that, so I'm going to change that x from -20, +20 to over here at the -2, +2, and you notice that it still looks pretty bad. So what's happening is it's oscillating infinitely many times there. So in this case, the limit does not exist either. And you could change that to from 0.5 to -0.5 to 0.5, and you'll notice that you still sort of have the same mess that's happening there in the center. All right, so here's an example we're going to look at. And we're going to need to graph this one. So let's go ahead with our calculators and put this one in. And we have -1 over x squared. Okay, let's turn off the previous, and I'm going to do a zoom 6. Okay, and so we see something sort of strange going on, but we might need to take a closer look. So I'm going to take off some of the top Y. We don't need to go as far in the Y. And then we'll do the same in the X direction and probably change this. Let's change this to something like a -15 because it looks like it keeps going. Um, change my Y max to 1. And let's see what happens here. Okay, so we see a graph. Get a little closer look. Let's change our X values. Change that to -5 and +5. All right, let's just look at a graph here. Okay, so hopefully you're going to notice that this does resemble something that we did previously. This time, instead of instead of f of x becoming infinitely large, it's becoming infinitely small as x approaches 0. So this would be an example here of the limit does not exist because as x is approaching 0, f of x is becoming infinitely small. All right, and here we go. Another example. And we're going to take a look at this one on the graph. Okay, so we have negative absolute value, and so to pull up absolute value, we go to Math, go over to Number, and press Enter on number 1. We're looking at the absolute value of 2x, and dividing by x. Okay, and I'm going to do a zoom 6 on this one. There we go. It does look familiar. Let's get a better look at the graph. Let's go to the window and change our y minimum to -4 and our y max to +4. Okay. So to find out what's happening, let's go to trace, and we notice that at x equals 0, f of x is undefined. And then we have pretty strong evidence here that it's, from one side, it's approaching, looks like y is approaching 2 from one side, or it actually is equal to 2, or f of x is equal to 2. But from the other side, f of x is approaching -2. So we have inconsistency. That's the case that we talked about, the second case, where where it's approaching and f of x is equal to L in one case, f of x is equal to M in the other case. And so in here again we have that the limit does not exist. Okay, and then we've got one more example. And again, we're going to look at a graph. Okay, so we have cosine of pi over x. And since we're dealing with cosine, let's do zoom trig again. All right, so it does look like we have some oscillating going on there, but we need to move in and get a closer look at what's going on. So I'm going to go to my window, and I'm now at -2 pi and at 6. So first of all, we're going to 0, so that's easy to go a little bit on each side. So let's change that to -2 and +2, and we are going to scale by 1 instead of pi over 2. And let's change this minimum to -2 and +2. Okay, and now let's look at a graph. Notice that even though we zoomed in quite a bit, we're still seeing all of the oscillation going on there close to where x is equal to 0. So let's go in again and change our x's to -1 and +1 and graph that. And you still see sort of the same thing. You see, just see more detail with lots of oscillation. Let's try it one more time. Let's try this as -0.5. And so let's make it really small. Let's try it at -0.1 and 0.1 and see what happens. And we still see sort of about the same thing that we saw earlier. So what we have going on here is that it's oscillating infinitely many times as x is approaching 0. So again, last example is where our limit does not exist. Okay? And that's my last example. One last thing, don't forget that I do want you to go back and work on that one problem, the piecewise function. It actually does have a limit to it. Let's see if I can find it. Here it is. Okay, so here on this piecewise function, we're looking for the limit of f of x defined by this function here as x is approaching -1. So I have the information here, and so we're looking for what is the limit of f of x as x is approaching -1. And we will talk about that in class tomorrow. And that's all I have for you for section 14.1.